Hello and welcome to this Aerospace Testing International webinar, which today is about innovative digital radiography and computed tomography solutions. The presenter today is Rahul Alreja, the Director of Global Sales and Marketing for VJ Technologies, a leading global provider of X-ray inspection solutions for quality control in a wide range of industries throughout the world. Rahul and his team at VJT are involved with bringing advanced technology, robotics, automation, and computer and machine learning to a variety of industries, including aerospace, specifically targeting quality control and product flow. He is the author of several technical papers, and Rahul regularly gives presentations around the world about the latest advances in the field of non-destructive testing, an area where VJT is constantly pushing the technical boundaries. Rahul is here today to talk to us about some of the latest developments in digital radiography and computed tomography, things like in-field CT, multi-part CT, automated inspection, and high-energy inspection. Just one quick thing, after the presentation, there will be a live Q&A session. So please do submit your questions during the presentation and afterwards as well for Rahul to answer. So over to you, Rahul. I hope you're doing well today and looking forward to your presentation.
Well, thank you, Ben, and welcome everyone. I'm glad that you guys were able to join us. Hopefully everyone's doing okay. I know some of you guys in Europe are still under some lockdowns, and hopefully we come out of that well, and hopefully I can provide you some kind of break from all of that and give you something to think about. So I figured I would start with a little introduction of our company, just to give you guys an idea. We've been around since 1987, so we're now in our 34th year, headquartered here in New York, looking after a variety of different industries. And we have always been focused just on primarily digital X-ray, now computed tomography. We do dabble in a few other fields, but I would say 98%, 99% of what we do is digital X-ray. And as you can see, we're in a variety of industries, from aerospace and electronics to automotive and oil and gas and nuclear. So we have experience in a variety of different areas. And what we do is we kind of bring that experience to the aerospace market, or any other market that we're kind of working in, but specifically for this webinar, is taking our experience from other kind of applications and bringing it into the aerospace world. So our group is divided into 4 different main divisions. One is VJ Technologies, which is the division that I'm speaking to you from. We're in the digital X-ray and CT solutions, whether it's systems or components, etc. The next division is VJ Electronics. This is a division that's primarily looking at electrical components, BGA boards, for things like on iPhones or laptops, etc. Then we have VJ X-ray, which is a division that actually makes X-ray sources for OEMs, primarily in the food and security space. And then we have VJ Inspection Services, which is where we actually offer to customers scanning capabilities, whether it's in the field or in our labs, where we can actually look at parts and do disposition on them. As I mentioned, we're global over the past 34 years. I think that number is a little bit old. We're probably over 400 people at this point. Headquarters here in Bohemia, New York, but we have locations all around the world. And so that's the group. And that I'm speaking to you from is VJ Technologies, as I mentioned. And we are known throughout the industry of having innovative CT and DR solutions. We're not just one-trick ponies or three-trick ponies. I'll show you some of that. What makes us unique is our imaging capabilities and our kind of software enhancement, and our ability to customize solutions, our ability to understand what actually has to occur for you as a customer, and then see how we can kind of fit around that. And this is just an example of some of the systems that we make. A couple of CT systems there, a DR system as well. So on to the topic of what we're talking about today. So what we found, especially in the aerospace world, which is rapidly growing, we have two multi-billionaires who've just entered into space in the past couple of weeks, in Richard Branson and Jeff Bezos. The development in the space in the aerospace world has been phenomenal. And what we found is that our kind of standard solutions don't really work all the time. So this is like thinking outside the box. And what that means is, for you guys as manufacturers, whether you're working for primes or tier ones or tier two suppliers, the idea is that when you're looking at NDT, specifically X-ray or CT, we don't want you to mold your process. Our whole ethos is we want to streamline it instead. So what that means is we want to understand from you guys, and we want you guys to tell us what actually matters in your process. What are you actually looking for? How detailed is your process? What are the steps in the process for your entire kind of manufacturing flow? And where would you ideally want NDT to fit, and how would it look like? So, what matters? Is it the time? Is it the time to actually produce the part? Is it the time to inspect the part? Or is it actually how quickly you need a solution? Do you need a solution tomorrow because you have a product run and you don't know what to do with it? And you can't really afford to send, thousands of parts to a lab to be tested. So what actually matters to you? Is it the size? Is it the size of the objects that you have to look at? Are you making a variety of part sizes, whether it's small little kind of 3D printed parts or large objects like large rocket motors? Or is it the size of the actual X-ray system? Do you have limited kind of floor space? Do you have limited ability to be able to, in your production floor, fit an X-ray system? Can you not afford to kind of construct a vault? So what is it in your process that you can afford to compromise on, what you can't compromise on? And how do we actually then fit a solution for you? Or is it the part handling? You're making large objects, or you're making objects that are delicate or filled with, propellant. So they have to be handled in a certain orientation or be handled with care. Some of them, might be explosive ordnance or things of that nature. And you have to be in a spark-proof environment with positive airflow. What are the things that actually matter in your process? What I'm trying to say is that whatever your requirements are, you don't have to fit into a small, medium, large, or extra large size box. The objective here is figuring out a solution that actually is optimized for your process. So don't mold your process. Don't think that you have to get your process to fit into what we as NDT providers have to give you, right? So if we're giving a DR CT system, don't think that, oh my God, I have to change my entire process so I can fit this specific CT system into my process. No. Why don't you think more like, how can I get an NDT system or solution fit into my process so I don't have to change it too much? So I figured I'd give you a few different examples from different kind of recent customers that we've had, all of them in the aerospace world, and how we've actually thought about innovative solutions or different kind of solutions to be able to fit inside our process, as opposed to making that process fit the X-ray system. So the first challenge is production CT for rocket motor inspection. So this customer is producing rocket motors for defense purposes. So various different diameters. They need to do CT to detect various flaws. The goal they have is that they need the CT systems to be able to keep up with production. That's 30 parts an hour. And these are rocket motors that you're talking about. Some of them are 5-6 feet tall. Diameters you're looking at ranging from a few inches to about 12, 14 inches for some of them. And they want to be able to detect 30,000 inch defects, so less than 1 millimeter. So the traditional solution, we got some samples, and based on lab studies, in order to get that 30 thou, we need about 6 minutes of scanning to ensure the detectability of that 30 thou. And yeah, traditionally we can always say, okay, you have the acquisition side, and then you have the reconstruction side, or the analysis and reconstruction side, and you can offload that into different PCs. And so you can get a few different PCs to be able to handle the reconstruction side, because reconstruction tends to take 15 to 20 minutes depending on the volume, and then you got to do your analysis on it. But you can do that separately from the acquisition. So the acquisition becomes a bottleneck, and you have about 6 minutes for acquisition time. So that means in order to keep up with that demand of 30 parts an hour, you need 3 systems to keep up with that demand, right? So that would be like a traditional kind of way of looking at it. Makes sense. You have a few different PCs for reconstruction and analysis. You can automate it, and 3 different systems will be able to meet that cycle time requirement. Now, that would work, except now you're paying for 3 different systems. You have a huge amount of floor space requirement, power requirements. You need trained operators that can look at 3 different kind of systems, be able to manage them, do CT on them, and potentially disrupt your product flow, because you probably have these coming on one kind of conveyor line. Now you have to split it into 3, either using robotics, and then be able to merge it back from those 3 back into the one production line as you keep going after the testing. So that becomes an unwieldy kind of challenge, very expensive. You have to be able to train the operators. And right now, I don't know about you guys, but we're having a challenge just finding people that we can kind of bring in, and people that can actually run CT machines and be able to kind of look at it. Those are more skilled. And so that's a huge kind of total cost of ownership if you have to do 3 systems. So we thought about it, and we came up with a kind of different solution, right? So we'll call it a creative solution. The idea here is scan 3 parts at a time in one machine. So as I mentioned, we have 6 minutes per part that we determined that we have to be able to, in order to reach that 30 thou kind of detectability. So at that cycle time, it was 10 parts an hour that we could do. Now, if we can do 3, we get to 30 parts an hour, and each one of those scans can take 6 minutes. We can't cut it down to 2 minutes because we just can't get the resolution that we need. So we designed a custom solution that can handle 3 parts at a time, doing helical CT, being able to separate out the volumes and be able to analyze each one individually. We have, as you can see here on the rightmost picture, different types of fixtures so that we can accommodate different diameters and be able to handle all the different sizes and the different diameters and the different requirements for the customer in one custom box. The box is small and optimized for floor space and layout requirements. We still have multiple PCs that are working and being able to do the reconstruction and the analysis side, but they can be handled by one operator, maybe 2 if you need it for backup. And they don't take up that much space on your floor. And, so you're not worried about downtime. You're not worried about any of that. And it becomes a very optimal solution for a kind of creative solution for something that could require a whole variety of systems otherwise. So here's a second challenge. A fast CT inspection with casting. So this is a 3D printed part. They want to get about 25 micron resolution in certain areas, and they want to be able to scan at least 10 parts a day. Doesn't seem unreasonable, right? So you're looking at about a 1 hour scan per part, maybe one a little over 1 hour if you do like a 12-hour shift, and get 25 micron resolution. But given the part dimensions, you can get that kind of resolution and be able to get that detectability in about a 2.5 hour scan. So you need 2 machines to keep up with this demand, unless you want to work 2 shifts and go crazy. So that would be kind of like the traditional way of looking at it. Or let's analyze the part. Let's talk to the customers and find out what are the areas that actually matter. Conduct ROI scans of that specific area to be able to do that measurement of 25 micron. Reduce the scan time by over 55%, and be able to then accommodate it in one shift and one machine. And what that looks like, this is that dark blue areas where they actually wanted to look at. The rest of it wasn't that important to them. And so we can actually do an ROI scan, get down to just that blue area right there, be able to do less than 25 micron kind of resolution, and be able to do, whether it's void analysis, porosity analysis, whatever they were looking at. This is 3D printed, so they were looking for porosity, which you can clearly see in these images. So rather than doing a scan on the entire part, do an ROI-based scan. So again, just some different ways of kind of looking at the problem. Just being able to kind of think outside the box a little bit. So third challenge. Now this is a rather fun one. So this is actually comes from the renewable side. So this is actually for renewable energy. That's a land-based turbine. So, not necessarily aerospace, but you guys do deal with kind of large objects and long objects. This specific object is 13.8 meters long. So you're looking at an object that is kind of unwieldy to manage. And as you can see, it's made up of different materials. So you have carbon fiber, you have glass, you have some foam, you have various kind of composites. And the idea is that they want to CT this and be able to see, first of all, the interfaces between the different materials, look for voids, porosities within the material, and be able to do 100% CT scan on this. So this is a scan of piece of this. This actually is right here in this light green area, if you can see it, which is that foam to bridge bond gap with the spar beam and the shell. And this is kind of the defects of the gaps that you can see. So in the middle is actually glass. And then you have this gap here that's in the different layers. And those are the kind of defects they were looking at. So as I told you, this is 13.8 meters long. Rather long object. So one of the ideas, which is a traditional solution, all right, we put the turbine blade or that spar beam on a turntable. You have a 30-meter tall room. And we do CT on it, traditional kind of CT, turntable base with a linear accelerator, with an LDA here, really nice long LDA, and be able to inspect this part, get the resolution that you need. Now the challenge, I don't think I have to tell you this, is the part is 13.8 meters long. How do you keep something like that stable on a turntable? Yeah, obviously you can have kind of clamping on the top, on the bottom. You may have even support structures kind of midway as you're holding it up. But then again, you also need a really, really tall room. You need the ability to bring that part in when it's being manufactured. It's not being manufactured in vertical orientation. It's being manufactured in horizontal orientation. So the part handling becomes a challenge. So we thought about it, and what we came up with, which was a slightly different solution. We create a rotating gantry-based system. So you actually keep the beam in that horizontal orientation. You don't need to rotate a 14-meter long object. Instead, we rotate the source and detector around that object. This shows it in a 450 kV configuration. We also had it in a Linux-based configuration that we created a kind of gantry that could actually rotate with a linear accelerator and a detector on the other side. And this is, a shielded kind of cabinet with conveyors and tunnels that will enable the process to stay the same. So you're not looking at taking a 14-meter long object, turning it on its vertical side or holding it vertically in some kind of custom jig, taking it into a vault, putting it on a turntable, clamping it down, being able to hold it, making sure it doesn't wobble too much, finding flat surfaces and being able to CT scan it. Rather than that, we just keep it horizontal and we create a rotating gantry instead. And it achieves the same results or actually better results, because you're not worried about the wobble specifically on a 14-meter long object. And it also is just a more palatable solution, something that fits more into the process of the manufacturing challenge. And now we have a rather unique one. So this is a large object inspection part 2. So this one, again, large objects. What do they mean in the aerospace side? It could be fuselages. It could be sections of a fuselage. It could be rocket motors. It could be a whole variety of different things to look at. And some of them require high energy. Some of them require limited angle CT. Some of them require different kind of techniques to be able to look at. This specific challenge was a rocket motor for prototype development. So this is it's called super fast rocket motors, and they can't be transported. They're prototypes. They're critical for defense. They're filled with propellant or material that the Department of Transportation won't really allow very easily on the road, so they can't really be transported to someone else's lab. But again, this is prototype development, so they don't need a dedicated system to be able to look at this, because they don't exactly know what the final product will look like, what the final product orientation will be. So it doesn't make sense for them to spend a few $1 million on a high energy CT system when they don't know what the parameters have to be. And you also can't touch the object because, as I mentioned, it's prototype. It's propellant based, it has propellant within it. And they have a whole variety of sensors lining the object, and they don't really want you to touch it because they're doing different kind of firings on it, and they want to make sure that they don't introduce outside variables to that. So, but they want CT. They want to be able to see this thing and be able to analyze it fully, non-destructively. So when they do different firings, or when they do run different tests on it, whether it's environmental tests or they're actually firing the rocket motor, but it's kind of stationary, they want to see what's going on inside rather than just looking at kind of models and based on CAD data. So they wanted to be able to do CT on it. They asked for resolution about 1 millimeter. So the question is how? Now you have this large object. You can't really transport it anywhere. And it needs to be handled with a good amount of care. So the idea was, let's take a solution to the field. Now, if you recall, my previous slide, I'll just jump back there. Showed you like a rotating gantry system here, right? So it's got a wheel. It's got it kind of, this is sitting in a cabinet. But how do you now take that into the field? So we designed a gantry here that actually is portable. It actually can be taken into the field. What you see here is a flat panel detector. On this side was a Betatron, actually, which is kind of like a portable high energy source. And this is a CT system that can spin around the object and be able to capture CT on that large rocket motor. And again, this is being taken into the field. So they can't send the object to us. So we decided, all right, we'll take a CT system to them. As I mentioned when I started, we apply learnings from various different other industries that we are involved in, and we try to bring them to deliver kind of unique solutions for customers. And this specific one was actually designed for a utility here in Manhattan, in New York. And just before you think that this is just a concept, we actually deployed this in the field. So just to give you a little background, this is actually in Manhattan. This is a manhole right here. You can see like a nice New York City police car right back there. And what you're seeing here, in Manhattan, we actually inspect feeders. So Manhattan and most older kind of cities on the Northeast Seaboard here in the US, they don't have overhead power lines. So power lines are all driven underground in these kind of large pipes and large casings. And they're looking for areas where they're splicing these copper conductors. I won't go into the details for what they're looking for, but we were actually able to take this CT gantry that we designed for this utility and bring it out into the aerospace world looking at a large rocket motor. I'm not allowed to show you those images, obviously. As I mentioned, it's prototype development and critical for national security. But I can tell you that it was considered a roaring success. To give you an idea, just about some of the innovative things that we can do, this specific gantry, as you can see, it's multiple parts. It actually sits on rails, so you can actually traverse the entire length of a large object. It's powered by different motors, so it actually can automatically traverse and be able to do full kind of CT scans. This specific gantry, as I mentioned, was going in manholes. Now, manhole opening is only 28 inches in diameter, so every part that we put into the manhole, into this chamber, had to be able to fit through a 28-inch diameter opening. So this specific gantry is actually designed like a Lego kit. It can be disassembled into various pieces, taken down into a manhole, and reassembled in the manhole around the pipe. Again, not touching it, because we can't touch these pipes either. Some of them have low voltage that they float across in order to, kind of counteract any corrosion that might develop, or rats or anything else. So they actually have like a low kind of voltage that goes across the line. So they rather that we don't disrupt or touch it. So everything that we do is assembled around the pipe without touching that specific pipe, including the rails. And then we actually calibrate this within that manhole and then traverse the pipe. We use that same principle here for the large rocket motors in the field. This is a very, as you can see, how we get that precision on this gantry is actually we designed it as a gear almost. So it's got teeth that are all spaced out evenly. So we can actually do measure exactly with the rotation axes, the degrees of rotation, and determine what angles we're taking, which is critical for CT and valid kind of reconstruction. What's also unique about this challenge, which almost is apparent in these images, so this is actually designed to also do limited angle CT. So the problem is sometimes in the field you have obstructions, right? So you might have a large rocket motor or a large pipe, and so the rocket motor is usually on stanchions that are holding it. There may be walls, there may be other things that are around it. The idea is to be able to take your CT scan while not necessarily getting 360 degrees around the circumference of the object. So we've developed techniques that do limited angle. So you can take, 25 degrees of clearance here. So we can do 25 degrees of scanning here, maybe 40 degrees here, 30 degrees on the bottom, 20 degrees elsewhere, and then be able to stitch that data and reconstruct that data into a CT volume. Obviously, the more projections and the more kind of slices that we can acquire, the better off we are. However, like I said, that's not always possible in the field. So the algorithm actually is able to use what we call a priori data, which is when we're inspecting these kind of objects, the customer, you guys typically know what's in the object, what kind of materials we're going to be encountering, and what the expected configuration of that is. So we can use that data and tweak the CT reconstruction and the CT kind of algorithm in order to use that data to create usable data sets with just very limited angles and projection data. And that's a really fascinating kind of technology, something that has applications beyond just field inspection. It's got applications even potentially for high-speed inspection or inspection of different kind of multi-material or large objects, etc. The ability to use all the data that we know about the manufacturing process, about that, the part and the materials that are inside of it, to be able to create better CT data. And there's things that you can do with dual energy, which we've looked at, where you can actually take CT data and scan it twice almost, once at a higher energy, once at a lower energy, and be able to use the difference between the projections from those two different scans, and then be able to use that to do material discrimination or just look for low density objects or high density objects within that specific part. So as I mentioned, there's a whole different kind, there's just different ways of looking at CT or DR solutions for your process. The goal is understanding that process and us being able to, as solution providers for NDT, us being able to accommodate your process. We don't, like, as I mentioned, you don't have to fit into a small, medium, large, or extra large size box. I hope you can see from this that the idea is, how do you take what you know and what about your process can change and what about your process cannot change? What are the important features, whether it's the size, the time, the part handling, and then figure out a CT solution or a DR solution that fits around that process. That we are very open to kind of discovering any problems you guys might be having, any kind of unique areas where you thought it's not going to be possible, we can't fit any kind of CT system in here. I can tell you that there's different ways of skinning that cat. So I hope that this kind of opened your eyes up a little bit to some of the different ways that you can look at NDT solutions and having it fit your process as opposed to having your process fit the NDT solution. If you want to learn more, please look at any of the websites that we have below. Thank you.
Great, thanks, Will. That's really interesting. Some really interesting and creative solutions there to some of the problems that I guess people are coming to you with quite often. Are they always, these problems, are they always around size and proportions, or is that the most common thing people have, concerns and challenges with?
It's a good question. So there's different ways to kind of look at it, right? So it's not just size, or it's not just I know I kind of went into length and large objects, small objects, but
Sure.
As I mentioned, there's other challenges where you have multi-material. There's other challenges where you have, time to be able to inspect, because you need to be able to keep up with production time. And there's other challenges that I haven't even mentioned where the customer has a very unique kind of geometry, and you can't actually do a full 360-degree kind of around that part, because the width of that part is sometimes really, really massive. So you have like a base plate or some other kind of object there where you can't penetrate no matter what energy you use. Or if you use really high energy, you're going to blow through everything you need to look at. So then there's other things like planar tomography or laminography kind of techniques, which you can look at. So it really depends on the actual different parameters of that specific object or of that specific case.
Okay, sure. All right. I know we've got some questions stacking up here, but I'll just ask you one more. I mean, some of these solutions are very, they're bespoke, right? They're one-offs for clients. Yeah. So how long does it take? How long does it take you to develop that? You know, from someone coming to you with something and then you delivering it on site and.
That's also a very good question. Obviously, some of these can take a good amount of time to develop, but I can tell you that we have had for that last one that I showed you in the field gantry for a large rocket motor inspection. We had a solution from problem statement to in the field ready deployable in 2 weeks.
2 weeks.
2 weeks, our team was out in the field actually running the first iteration on that scan. We have had cases where, you know, if you're designing a custom system like that rocket motor that I first showed with the 3 rocket motors, etc., that development can take 6 months, sometimes a year, depending on what level of automation is needed, what level of kind of part handling, and how sometimes it's even clearances, right? So sometimes, you know, customers have, you know, we have certain kind of allocations and certain kind of parameters we have to follow. And because these are bespoke, sometimes they need kind of, you know, to be able to think a little bit creatively, even on that side. So we work with customers to kind of hold their hands through all of that and determine what parameters, again, within not just the manufacturing process, but even on their approval process that they can kind of go with. So some of that kind of adds up time. But typically, solutions are, like I said, we can do things in 2 weeks. Some of them have taken a little bit longer. And we also have the ability where we have mobile labs or mobile kind of environments where if a customer has a need that, say, we know you're building like a bespoke solution for us and it's going to take like 8 or 9 months to develop, but we have some kind of first phase and second phase kind of articles coming out, small batch kind of production. We have the ability to take a lab to their site on a 53-foot trailer or on a 40-foot shipping container and have them have a mobile lab that's, you know, maybe even sitting in their parking lot that we can power off of a generator to do CT or DR as we kind of develop a bespoke solution for them.
Okay, sure. Yeah, that was one of my. We'll take some of these questions that are stacking up here. I don't want to monopolize the time too much, but that was one of my questions actually. Was do you get people who call up and say, "I got an emergency CT problem. Can you come and do it?" I guess you do. Anyway, this one here
always an emergency.
It's always an emergency. They're always on it yesterday. Okay, so Richard Joseph, I'm going to apologise in advance for my pronunciation. Swarovski is asking here. Look, quite a general one, really. But is innovation, in your view, driven internally or by the client in this area? Is it a push or pull thing? I guess.
Yeah, it's a very collaborative effort, actually. You know, part of the innovation is, okay, a customer comes with that kind of unique challenge that they have, and said, hey, we can't find anything that's kind of off the shelf available to do this. Can you help us? But sometimes the solution is more innovative from our side, where we're looking at, okay, this is how this has typically been solved. We know this will work. We know what this will cost, but we might actually have a slightly different way of doing it, which will provide you more value. So, you know, to take an example, a customer may say, okay, I have a vault. I need, you know, to upgrade some equipment with manipulators. And, you know, this is how my process works. I just need to kind of upgrade and do all that. And sometimes we'll ask them and say, hey, look, what is it that you're trying to achieve? What about, you know, in the next few years? Are you looking at producing more parts, or are you looking at producing a variety of different kind of parts? And maybe you want some kind of things like part identification or barcoding or collision avoidance, or, you know, things of that nature where they may not have even thought of it. But because of our experience from a different variety of industries and different kind of bespoke solutions that we've developed, I think that innovation can actually come from both sides, because both parties bring different things to the table. And I think having that kind of collaborative environment between our engineers and the customer's engineers is what allows that innovation to thrive.
Sure. Okay. So the next question here is from Adrian Loggin, who's asking about the turbine blade, the renewable piece of equipment, the spar beam. He wants to know what the width of the blade is and what was the resolution of the measurement that was being made.
Sure. So good question. Good to talk to you again, Adrian. So the width of that spar beam, if you look at the cross section, which is like the diagonal, the longest diagonal, the longest kind of core through it was about 42 inches, I want to say. 42 inches. So you're looking at just over kind of a little over 3 meters in width. And the resolution that they wanted, we got down to, so it actually was different resolution in different areas of that beam. So there were certain areas where 10 millimeter resolution was fine. There were other areas that they needed 1 millimeter resolution. Less than 1 millimeter was a challenge, just because of the dimensions of the object and because of how long we actually had to be able to inspect it. So the smallest was actually about 1 millimeter, which they were fine with. Some of the areas, in order to save time and because there was enough tolerance built in, was 10 millimeter resolution.
Great. Okay. Thanks, Rahul. The next one here is from Logan Freeman. He's saying, we've talked a lot about solutions. That's what we tend to do. What are the most common source and detector setups that are being used within CT setups that you deliver?
So that's a good question. So in the aerospace world, it used to be all microfocus, right? So everyone wanted 225, maybe 300 kV microfocus with some high resolution flat panel detectors. And that was great. But now, because you're looking at lighter weight materials, you're looking at carbon fiber, titanium. But now in the aerospace world, we're looking at larger objects. People want to go faster, further, stronger. So they're actually making them larger, a little bit more dense, a little bit, using more things like Inconel and other kind of alloys like that. So I'd say that the energy range runs the gamut from anywhere from about 130 kV microfocus, where you're looking at small little kind of 3D printed parts, some small electrical components. Traditionally, we see a lot of interest in that 225 to 300 kV microfocus. Some of it is at 450 kV kind of standard focus, some 600 kV, especially for like turbine blade inspection. And then we go into high energy, 3 MeV to 9 MeV for a large rocket motor and large assemblies. We actually have systems that can be configured with dual detector and dual source. So you can have a 600 kV with a 300 kV microfocus, giving you a lot of flexibility within that system. And then dual detector, which would be a flat panel, as well as an LDA. A lot of customers are okay with just the flat panel because it's faster to do like a cone beam CT and reconstruction. Some of them for finer resolution or for wider objects, they don't want to do like an offset CT scan. We use LDAs that are longer to be able to capture the entire width of that object. So it's very dependent upon the actual objects that are being inspected and what the desired outcome from the customer is. Like I say, no one solution works for everyone, so we actually tweak it based on what's needed. Okay,
great, thank you. This is more of a statement than a question from Claudio Deru, who's just saying that what you're talking about is like creating a tailored CT system for the article that's being analysed, which I guess is kind of the gist of your entire presentation, right?
Yeah, it's this. Absolutely, we don't think that it's one size fits all, or maybe 4 size fits all. I think our whole ethos is that you can customize and you can build different types of CT for the application. What makes the most sense for the application is what we should use, as opposed to saying, this is what we have, make it fit for you.
Okay, cool, thanks. This next one here, I don't know if you can see it on your screen, Rahul. You familiar with that term, terabyte technology? Is that?
I do not know what terabyte technology is. I'm just going to do a quick Google and see.
I was gonna do that, but I didn't want to hear everyone tapping away on my keyboard.
No problem. So
maybe Vitali, if he's still on, he can.
Yeah. So terabyte technology, I mean, the only thing I know about terabytes is large kind of data. But terabytes of data, I'm not sure I know exactly what that is.
But data analysis. I don't know.
Yeah, so to diagnose materials in manufacturing to reduce manufacturing defects. So I'm assuming that looks like big data analysis type is my question. I'm sorry if that's wrong, Vitaly. That's kind of my assumption based on that. So yes, we are absolutely looking at big data. That's been one of the big kind of buzzwords. Obviously, with big data, the challenge actually is not collecting the data, because everyone has oodles of data, but it's actually being able to deliver or derive kind of outcomes from that data, to be able to analyze that data and see things that actually make sense out of it. So in those areas, we are actually looking at, rather than like just rigorous kind of statistical analysis. So we actually work with different kind of universities and labs. And when we have kind of big data projects, we have about 4 of them that are ongoing for different industries right now. One's for munitions, one's for the aerospace side, one's for automotive, and the last one is for electronic components. Looking for trends, looking for the goal obviously is, like Industry 4.0, everyone wants like a self-fulfilling kind of system where the system will know what the material is, what the properties of that specific material is as you're casting or making the part. Here's CT data that after you cast the part, here's where we're finding defects. Now we have like environmental data and we know material properties, and be able to analyze that and say, okay, so we got to slow the speed of this pour here. We got to do some more gating here. We got to do this on the part, and be able to kind of self-evaluate and be able to self-correct. We are a long way away from that, I would say, but we are absolutely interested and working towards that goal. And, machine learning and other kind of AI algorithms are certainly kind of helping towards that. We're partnered with certain institutes to do that, as well as developing it on our own.
Great, thank you. I hope that answers that question. I've got another one follow up here from Claudio, who, interestingly, he wants to know, I guess, how cheap can you go? Is this type of technology expensive or can you, do you apply it to low budget projects in universities? You did just mention universities. I mean, you're not going to say your lowest price online, are you, on the internet? But what do you commonly supply to university labs and workshops?
You'd be surprised, right? So we actually have products that we've developed specifically for universities for kind of low-end kind of environments where they're looking to kind of get into CT, whether it's small casting houses or kind of universities that are looking at teaching students or being able to expose students to different kind of materials or kind of manufacturing. So it's our Veda core product that actually starts at about $120,000. As opposed to CT systems, which can be north of $450,000, $500,000. So it's a tremendous value. It's about like 25% of the actual cost. And then we even do smaller systems than that. We also do it as a service. So sometimes cash flow or various kind of projects don't allow for capital expenditure. So we can do that as a service. We have a whole bunch of creative kind of financing and other areas. So if you're interested, certainly reach out. We can certainly work something out.
Cool. All right. Well, that tidies up all the questions from the audience. Thank you, everyone, for those. Some great prompted some great insights there, and it's great to engage with people and know that you're listening and that it's provoking some thought. I've been really impressed by that, Rahul. I mean, what impresses me the most is I always assume this is a very sort of delicate technology that can't be sort of manipulated too much, but you've shown some solutions there which are really surprisingly robust and flexible in where they're deployed and how they're deployed. Is it kind of a bit wild and wacky, or not that wild and wacky? I guess it's just what you do.
It's a little bit of both, I'd say. It's we like the challenge. It's really fun for us. We like to kind of again, think outside the box, look at things differently from other people, and be able to see the goal at the end is to make the life of the customer easier, not harder. So whatever we can do to make your guys' lives easier, that's what we're working on.
Great. Okay. Well, I think we're finished there, unless you've got anything else to add, or are you happy with all?
I'm good. So thank you all for listening, whoever stayed till the end. Hope you got something out of it.
Great. Yeah. Thanks again, everyone, for tuning in, those who did. And the webinar will, of course, be available to watch via the Big Marker platform and on the Aerospace testinginternational.com website. After this, you'll all be emailed through a link, including those of you who aren't watching at the moment. Yeah, thank you all, and take care, and enjoy the rest of your day. Thank you again, Rahul.
Thank you.